In this video, let's review applications of derivatives. Let's start with particle motion and position. Position is often abbreviated x of t. The first derivative of position is velocity. That's often abbreviated v of t, which is also equal to x prime of t. And then the second derivative of position is acceleration, which is the first derivative of velocity, is abbreviated a of t, and here it is equal to v prime of t or x double prime of t. Speed is your absolute value of velocity. We have a particle speeding up when acceleration and velocity have the same sign. And we have a particle is slowing down when acceleration and velocity are opposite signs. So then one will be positive and one will be negative. We have a particle is stopped when the velocity is equal to 0. When you see the word instantaneous velocity, you've got to think of derivative. So that would be x prime of t. When you see average velocity, you want to think of slope, which is just the change in position over change in time, or it's equal to 1 over b minus a times the integral from a to b of v of t dt. Your total distance traveled will be the integral from a to b of the absolute value of v of t dt, and displacement is the integral from a to b of v of t dt. Final position is starting position plus the integral from a to b of v of t dt. We've taken a look at these next two theorems, but here's just a little bit more to add to them. If a function f of x is continuous at every point on a closed interval a to b and differentiable at every point of its interior from a to b, then there is at least one point c at which the instantaneous rate of change is equal to the average rate of change. This is the mean value theorem. And so we can see that somewhere right here, this is our instantaneous rate of change, is going to equal the average rate of change. Extreme values. These are known as your maximums and minimums. There are two types, relative and absolute. So absolute extrema, these occur at critical points or endpoints. If a question does not use the word relative or local, then it's referring to the absolute. And in order to find the absolute extrema, you'll need to do a candidates test, and you'll need to show that table as justification on the AP exam. Your critical points, of course, we know to set the derivative equal to 0 and solve for the variable. We can do a sign chart with your critical points to determine if they are a relative max or minimum. All right, next we'll take a look at the characteristics of f, f prime, and f double prime. Just give me just 1 minute while I erase a little bit. All right, I want to show y'all my little chart. Right here, I've got three functions. I've got this first one in red. This is my position function, my f of x function. It's this cubic function here. Of course, the derivative of a cubic is a quadratic. So I found the derivative of that cubic, and here in blue is the quadratic. The derivative of a quadratic is a linear. And so in green, this guy right here is the derivative of my f prime of x, sorry. And so I've got I've got position, I've got velocity, I've got acceleration. I've got my position, I've got my first derivative, which is this in blue, and then my second derivative, which is in green. Okay, so now let's take a look at these characteristics. It says if f prime of x is positive, so I'm going to highlight some. If f prime of x is positive, so I'm looking at this piece right here, that is above the x-axis, then f of x is increasing. I match that up with this segment right here. So we can see that if my f prime of x is positive, f of x is increasing. Likewise, it says if f prime of x is negative, so then I'm looking at this piece and this piece. That's going to be where f of x is decreasing. It'll line up exactly with these two segments. Okay, next up we have a relative minimum and relative maximum occurs when f prime of x changes from positive to negative. So we're looking at a relative max, that would be right here, and that's going to be where f prime of x changes from positive to negative. So we're going from positive to negative, and that'll line up with my maximum. We have a relative minimum. This is going to occur when f prime of x changes from negative to positive. So I'm going from negative to positive, and that's where I'm going to have this minimum in my f of x graph. We have a relative minimum occurs at a critical value where f double prime of x is positive. So if I'm looking at this minimum right here, that's going to line up with a critical value where f double prime is positive. So I have a minimum here. That is where my f double prime is positive, to where it is above the x-axis. And then we have a relative minimum. Let's see, we already got that one. A relative maximum occurs at a critical value where f double prime of x is negative. So I've got my maximum where f double prime is negative. So all of this is, sorry if that's kind of sloppy. Let's see if I can try that again. That's going to line up, my maximum here is going to line up where f double prime is negative. Okay, I'm going to erase. Let's see, I think we're right here. If f double prime of x is positive, so we're looking at this piece right here, f double prime is positive, then f of x is concave up. Look at the concavity here. We can see it's concave up. If f double prime of x is negative, so now I'm looking at this piece of the graph, we can see f of x is concave down. If f prime of x is increasing, okay, I'm going to erase and we'll take a look at this next little piece. If f prime of x is increasing, so my first derivative is increasing, I'm going to go ahead and see right here, this piece is increasing, then f of x is concave up, and that's true. That's concave up. And then if f prime of x is decreasing, so I've got a negative slope, we've got concave down. All right, next up, if f of x is concave up, so I'm looking at this piece in blue, then f double prime of x is greater than 0. Well, f double prime of x is above the x-axis. If f of x is concave down, that's this piece in red, then f double prime of x is less than 0. That's right here. And I forgot to read off that tangent lines to f of x are going to be below the curve where your function is concave up. And of course, if you wanted to draw a tangent line anywhere, it's going to always be below the curve when it's concave up. And then tangent lines will be above the curve where it's concave down. All right, next up, we're talking about a point of inflection. So I'm going to erase some of this stuff. My point of inflection is right here. That's where I change concavity. So let's see. It says a point of inflection occurs when the second derivative changes signs. Does that line up with where my second derivative changes signs? Absolutely. I'm going from, let's see, positive to negative, and that's where that point of inflection occurs. Or if it changes from negative to positive. And it says, which is the same as f prime of x changing from increasing to decreasing. And so on our f prime, we can see we're going from positive, or I don't want to say positive, but I want to say increasing to then on the right side decreasing. And again, that where it goes from increasing to decreasing, that's going to line up with that point of inflection, which also lines up with where my second derivative changes from positive to negative or negative to positive. The last thing, it says an absolute global extrema can occur at endpoints or critical points, and which means use the candidates test. All right, the last thing, let's just take a look at. These are just some strategies when working with related rates problems. First, always try to understand the problem. Develop a mathematical model of the problem. Write an equation relating the variable whose rate of change you seek with variables whose rate of change you know. Differentiate both sides of the equation implicitly with respect to time, and then substitute values for quantities, and of course interpret the solution.